Hi class. So today is going to be about automatic differentiation. So specifically, we're going to do forward mode automatic differentiation via a high dimensional algebra form. So there's different ways to kind of look at this problem of how do you start to do automatic differentiation. And I think that this way of looking at it through algebras is actually the most accessible because it's just kind of straightforward mathematics that gives you a new form of automatic differentiation. Um, so uh, where this all comes in, right? Like we're in this general picture, this general story, is that we started by just kind of looking at these physics informed neural networks, right? And we're like, okay, these physics informed neural networks that give us this ability to include data with dynamical systems, and use our PDE knowledge as like a regularizer for our data, and that's great, but in order to actually get something working well, right, we're going to need to do two things. One is we need to understand, what how differential equations work better, which was the topic of our previous lecture, right? And the next thing is we would just need to start understanding what's going on with automatic differentiation, right? Because the core of a machine learning library like TensorFlow or PyTorch is automatic differentiation, right? That is what a library that it is. I would even go as far as to say, TensorFlow is a library for automatic differentiation and not machine learning, right? You can do machine learning with it. It's probably one of the main use cases of it, um, but it's not one of the main use cases of automatic differentiation. It's one of the main use cases of TensorFlow, but it is not necessarily a library for machine learning as much as it is a library for automatic differentiation that happens to be widely used by people doing machine learning. So what we're going to start to go into today is what is automatic differentiation, right? And it's this clever mixture of computational science and mathematics, right? So it's right at this boundary, and we're going to ask the questions of how do we represent derivatives and how do we calculate derivatives in a highly efficient way? Because remember, when we're doing the physics informed neural network, we're doing stochastic gradient descent over something that is defining derivatives of a neural network. So that needs derivatives of derivatives of derivatives of derivatives, and it needs to do it really fast. So, when I was behind the scenes saying, let's call this train function from flux, what are the things that were going on? And if we understand what was going on, then we can understand how to expand it and then hopefully make it better. For example, do automatic differentiation with ODE solvers involved and with PDE solvers involved. So that way we can use more information about classical techniques. So this is where we're going to. And today what we're going to do is forward mode AD. The forward mode AD is the version of automatic differentiation which is efficient when you have like 100 parameters or less. And we'll see why. We'll be able to understand where that relationship really comes in, and the order of the calculation. Um, but the first thing is, first we have to understand, why do you want to do automatic differentiation in the first place? And the real key to automatic differentiation, like where it really comes from, is not necessarily doing a faster computation, but from trying to do a more correct computation. And so the reason for this is because floating point numbers are not real numbers, right? The floating point numbers are relatively scaled numbers that represent real numbers. So, what do I mean by a relatively scaled number, right? So, we've gone over a little bit before that if you look at the floating point number representation, right? Let's like pull this up a little bit. You'll see the same figure everywhere, where you have a floating point number is something with significand, and it has a base and to an exponent, right? And so when you actually represent the digits of a floating point number, what the way that you represent them is you have some bits which are for you have 1 bit for the sign, so whether it's plus or minus. You have 8 bits for the exponent, and then 23 bits for the mantissa or the significand, right? So you essentially have 1 bit, you know, which is plus or minus, and then you have 23 bits times 10 to the And then what's up here is an 8-bit representation. Right, so what a floating point number at its core, like when you write down 0.1, what this actually translates to is plus, 0.1000000000000. That's not the correct number of zeros. We'll see in a second. Times 10 to the minus 1. So we'll actually move this over to be in 1.0. And then yeah, so this is actually, because I wrote it down as 0.1, this won't actually be correct. 0.1 will have an aberration at the end. Why will it have an aberration at the end? Well, because you cannot represent 0.1 in terms of the basis of things that are representing, in a 2-bit basis, right? Because, for example, you have two, right? So when you have a 2-bit basis, then you have to represent everything in powers of 2. And so we have something that is like 2 to the minus 2, or 2 to the minus 3, 2 to the minus 4, right? So we're going to do something like 2 to the minus 4 plus 2 to the minus 5 plus 2 to the minus 6. Right, and if you do this, you'll see that, nope, that's too high. Right, so you'll have an expansion that you can write out 0.1 in, and it'll be correct to the number of decimal places that you have in floating point, but it won't exactly be 0.1 because this is one of those values you can't represent. Um, this exact point seems like a minor detail, but we'll show today how it actually becomes a real big detail. Right, so this is a floating point number. Right, usually this is in the background. This is the 32-bit version. When you go to the 64-bit version, these get a little bit larger, but this is essentially what's going on in the background. You have a number that can represent some digits, and it can represent a base, right? Now, the interesting thing about these floating point numbers then is that they're relatively scaled, right? The reason why the way that they're relatively scaled is because you can change this exponent number, right? You can change this exponent, and you still have the same number of relative digits in that area, right? In that relative magnitude. So the representation is more about how many bits, or how many decimal places can I represent with a number. It's not necessarily like the smallest number you can represent is X, right? There is a smallest represented number, but that's not necessarily something to think about in your calculations, because it's more about, how many digits do I have over here? Because once you start hitting that spot where you've fallen off from digits, that's where you start to introduce this floating point error. Right. And you can almost immediately see where some of these difficulties are going to come from, right? Because if you take one of these numbers as 10 to the 5th and you subtract off a number that's like, 0.06623, you do something like that times 10 to the minus 2, or 10 to the minus 5th or something, right? Then the first thing that you have to do is you have to put these in the same basis. And so you're going to have to chop off a lot of digits in one of them to correctly put this in the right basis, right? You're going to have to do something like this, right? If that's 10 zeros, right? And then that's how you're actually going to do your arithmetic, where you have the correct signs, and then you do the subtraction between the two significants. But now you can see where the error is, right? Because the error is that we only got 2 of the digits out of all the other numbers that we did have here, right? So the key to floating point correctness is not the size of the absolute size of the values. It is the relative size of the operations that you're doing, right? If your operations are all relatively the same size, then you have quite a few digits. If they're relatively not the same size, then as you go orders of magnitude 2 apart, those are digits that you're losing in your computation from the total number. So the thing to keep in mind here is, well, the first thing to understand is then, what is the total number of digits that you have to deal with before you start chopping off digits, right? So if your computation was perfect, if you're representing the number perfectly, how many decimal places do you have? And how many decimal places do you start to lose? And this answer is given to you by epsilon of the floating point number, which is 2 times 10 to the minus 16, which is the smallest number such that 1 plus epsilon equals 1. Well, it's the smallest number for which that's not the case, actually. So it's a little bit tricky in its definition, but this is essentially there. Um, okay. So floating point epsilon tells us that if you have two numbers that are 16 digits apart, you will not be able to represent their um, you will not be able to represent their operations anymore, right? So if we do something like 1.0, so let's do something like 1.1 plus epsilon of or 1.1 plus 1 minus 1e minus 16, you see that the answer is 1.1, right? It's not 1.1 plus a small number with some error. It's literally 1.1. So if you add something that's more than that distance apart, you are going to have done no computation. Everything is junk at that point. Um, so that gives us a relative size for how big we have to store our computation. And the key here, right, thinking about what I just said before, that all floating point arithmetic is relatively sized, you have a different epsilon for all these different values. And notice how this is going to change, right? So if you are trying to add something to 1.0, it better be something of the size greater than 1e minus 16, right? 1e minus 15 is you'll get one decimal place digit of accuracy. If you move down to 0.1, you have relative scaling. You now have something times 10 to the minus 17 for your accuracy. Then you have times 10 to the minus 18, right? So it's not you do not need to necessarily keep the absolute values at a specific level. I mean, some things can help, right? So trying to keep things around one and using non-dimensionalized numbers can help some computations, but the general idea of when thinking about your floating point errors is more so about the relative differences than the absolute values of the floating point numbers. Right? If you're at 0.01, then you better not have things at 10 to the minus 18. Whereas if you're at 10, you better not have values that you're adding that are 1 times 10 to the minus 15, right? It's all about whether you have a 16 decimal digit relative difference. So this issue is essentially what causes round-off error. So round-off error, by definition, is the error that is introduced in floating point numbers when you have this process get involved. So I showed a quick example there about how this can be pathological, right? So let's kind of type this out again. So let's do something like we write down a number times 10 to the minus 10 times 10 to the fifth, and then we have another number here like 1 point junk times 10 to the minus fifth, right? So the way that you do this operation then is you're going to want to change this number, right? So when we change it times 10 to the fifth, what we're going to do is we're going to stick a bunch of zeros in front of here, 10 zeros, and then we chop everything off. And then this is what we actually get to add together to do our operation, right? So then we add these together. We have 1.000002 or and I'm not going to do the whole thing out, but yeah, so that's how you do the operation, right? And so you see that right there that what caused this problem was having these relative differences that were large. So this really will come into play when we're doing subtraction. So we'll see how numerical differentiation is actually like the key. It's like if you wanted to build an example that gave you as much round-off error as possible, floating point or doing derivatives in floating point is like the best thing that you can do to do absolutely the worst. And so let's see this in action, right? So let's do the example x plus a small epsilon minus x. I mean, a first grader who is sufficiently smart will know that this is going to be equal to epsilon, right? Because numbers are commutative, right? They have the cumulative property, they have the associative property. So let's move this around, move epsilon out to here, do x minus x plus epsilon. This is equal to epsilon, right? Floating point numbers do not satisfy that property. They are not commutative and they are not associative because they have this round off error. The cases where they're not commutative is actually very obscure, and it has to deal with something that we won't mention too much of. They're called subnormal numbers. So subnormal numbers are numbers below which where you no longer have the standard representation. Um, there are some like numbers at like 10 to the minus 48 or something. There's like some weird numbers that exist in the floating point system that a lot of people kind of ignore because you can read the floating point spec for why they're there. So floating point always has these edge cases that are slightly different, right? So there's the fact that there's a negative 0.0. Why is there a negative 0.0? Because that actually gives you a log of a negative 0.0 is the limit as you go approach from the negative side as opposed to the positive side, right? So floating point has a lot of things that might look weird at first, but if you actually if you see the whole argument, you'll be like, yeah, that's required to do everything correctly. So what I'm saying about these floating point numbers is more about the general floating point numbers, like the standard ones you'll run into, though there are some non-standard ones around. Um, so okay, so for the most part, the commutative property is held by a lot of floating point numbers, but there are some that actually they fail on, and so compilers like LLVM do not do optimizations that require the commutative property. Um, and for definitely the associative property always pretty much fails, right? And the reason why the associative property fails is because this round-off error process changes the result of a computation. And so if you do a computation in two different ways, you can put parentheses in such a way. So like if I did this as x minus x plus epsilon, right? This is a case where if I put parentheses here, you can have a whole lot of round-off error, and then you have a non-zero result. Whereas if you do it like this, then you have epsilon as a solution with zero error, right? So floating point numbers are just not associative, and compiler optimizations cannot assume that they're associative without the user telling them specifically that they want the associative property in the optimizations. And the reason is because these examples with round-off error tell us that we have to write our programs in very specific cases or in very specific ways in some cases. And so compiler cannot necessarily assume associativity without breaking your code. Matrix multiplication or yeah, some of these operations in factorizing matrices, so LU factorizations, QR factorizations, are places where this fact is actually fairly crucial. For the most part, most codes that you write, you can probably treat it as commutative and associative and get away with it. Um, so okay, so here's going to be an example where the associative property fails, commutative property would fix this, but we aren't a compiler. So we do x minus x plus epsilon minus epsilon, and that should calculate epsilon, but it's not going to. So let's see the relative size and let's see that drop off process, right? So when I did this, we saw that we dropped off the number of digits that is the relative difference between the two exponents, right? So let's build an example to showcase exactly that process. So if x equals 1, let's let epsilon be relative size around 1e minus 10, right? So x plus epsilon will be correct to 10 digits. So it'll be correct for 10 digits, and it'll drop off the smallest 6 due to the addition. Yeah. And then when you subtract off x, you will be subtracting off all of the front digits. They'll be the same, right? So everything up to the point where this second number starts will be correct. And so we'll basically be able to take all of this and we'll be able to accurately subtract all that off, and we'll get epsilon, but we'll get epsilon back, except it'll be truncated at the spot it needed to truncate to make the exponents the same, right? So let's see this in action. So let's take a random epsilon, 7 times 10 to the minus 11, right? And now we do 1 plus epsilon, and we see that it dropped off digits, right? It dropped off this portion after the 5. And now when we do 1 plus epsilon minus 1, we get this value, right? And now let's actually look at epsilon minus epsilon 2. So if the commutativity and everything was perfect, this would be equal to epsilon. Instead, this is a value at 1e minus 17, right? Why is that one? Why is it at 1e minus 17? Well, because remember, the epsilon of floating point arithmetic is 16, and so when we're using the value 1, we get everything to the first 16 digits correct. So the first digit that's incorrect is the 17th digit. And there we go. We have an error that's incorrect to the 17th digit, right? So this process, this mental process of what's going on, is a very good way to think about, how you're going to be introducing errors in your calculation. And if you're doing a numerical analysis class, you'll then go into very, very deep details of trying to understand how these propagate and such. We're going to kind of leave it at that. Keep in mind the 16-digit rule. When you have float 32, it's an 8-digit rule. When you have float 16, it is a 4-digit rule, so don't use float 16 pretty much anywhere, other than in a neural network where you allow the results to be incorrect, but you train to fix that, right? So there are more pathological examples that you can do from this. So for example, catastrophic cancellation. That's how you spell catastrophic. Right, so there are these examples that you can put together, like instability in the quadratic equation, or if you write the quadratic equation in the incorrect way in a computer and you don't let a symbolic system fix this, then you can easily make it so that way you're subtracting off all of your digits, and you might have one or two digits correct and the other are junk. You can build even more pathological examples where you are subtracting off 16 digits, and so therefore you essentially have a random number generator instead of the algorithm you wanted. We'll leave that for a numerical analysis course, or you can look this up if you're interested. But for now, let's go into one exact example of where this kind of shows up, and it is in finite differencing. So finite difference is this idea where, this is the definition of a derivative, right? F of x plus epsilon minus f of x divided by epsilon. Take the limit as epsilon goes to 0. You have f prime of x, right? That sounds great in theory, but the example that we just did was literally an f of x plus epsilon minus f of x, and then, well, what happens when you divide by a really small number? Right? Well, what happens when you divide by 1e16? You still have error, right? But it's even worse, right? Because if you divide by a really small, so notice this, right? So we had an error, we get an error in that smaller digit, right? So here we get an error in the 11th digit. It does depend a bit on the random numbers you get, right? So here we get an error in the 11th digit, right? So now if we say, well, let's do the same process and then divide by epsilon, well, what are we doing? Right? If you go back up to what we were showing before, we're taking that result and then we're doing times 10 to the 11th, right? So we still have all the error. We're just moving our digits all the way back. We're just getting all of our digits back, but what we append on the end are just junk zeros. They're junk zeros in base 2, and so it's not going to come out as a nice number in base 10. We're just going to get the first few digits in decimal are going to be nice, and then you're just going to have a bunch of junk where the amount of junk is the size of what we just multiplied by, right? So if we divide by epsilon, and so now this thing is going to be size, so that way, well, it's going to be a good size junk, right? It's going to be junk that is now the same absolute size as what we had before, which isn't good, right? Because now we've just made our errors be big numbers, and so that's why I say that finite differencing is one of these pathological cases of floating point numbers, because you don't ever want to subtract two numbers that are nearby, because when you subtract two numbers that are nearby, then you only have the number of digits that is of what you only have the number of digits of how close this thing is. So if this spits out a value that is times 10 to the minus 15 away from this value, well, you're only going to have one digit correct, and then you're going to divide by a number that's like 1 times 10 to the minus 15, and so you get a number that's like 1 dot randomness, which is terrible, right? It's actually it's you can set this up to get basically all random number. You can build a random number generator out of doing finite differencing for your derivatives. So that's not good. Um, is there but is there a way to do this correctly? And the correct way to really think about it is to look at this process, right? So you have this process where you're taking a value and then you're taking another value times 10 to the fifth. You're taking two values that are nearby, and so what you want to do is you want to make the epsilon as small as possible, right? You want to make the epsilon as small as possible because it's only going to give you the correct derivative when epsilon is close to zero, right? So it needs to be as small as possible such that that's true. But every single time you make epsilon smaller, right? When you make epsilon smaller, you're going to be chopping off more digits you're going to be chopping off more digits because the smaller this value is, then when you put this up here, that's more zeros you put in front. So when are those two things balanced, right? When is the balance of putting more zeros in front finally, when is that balanced with the you want epsilon to be very small for the correct derivative? And that is balanced at, you can prove that you want both errors to be doing as both errors to be contributing equally for that to be the problem. And so if you have 16 digits, well, then you want probably 8 of those digits to come from round-off error, and 8 of those to come from getting the derivative incorrect by having too big of an epsilon. So what is the value of epsilon that would make it so that way you have half of the digits come from the round-off error? And the answer to that is just square root of epsilon, right? Because that is taking half of the exponent, right? 1e minus 8. So you can kind of show that there is this point of diminishing returns right about square root of epsilon, where square root of epsilon is some kind of key idea or some like principal area where that is the least error you'll be able to get from finite differencing. Right, so you want to do something where you're dropping off 8 digits instead of 16, right? And then you're going to introduce some error in your derivative, but you can show over the space of all possible functions that this is a good solution. So if you do have to do finite difference libraries, do make sure that you do this kind of analysis. This is for the forward difference. You can show, for example, that when you do central differences for the second derivative, or central differences for Jacobian, you should use the cube root of epsilon. So there's numerical analysis properties that you can use to show that what exactly the best epsilon should be. And the libraries in this aspect, such as finite different.jl, use these results. So how well does this actually end up doing in practice? Well, so there are different ways to calculate this derivative. So instead of using f of x plus epsilon minus f of x divided by epsilon, you can also do something like f of x plus epsilon over 2 minus f of x minus epsilon over 2 divided by epsilon, right? So you can do this. This is called central differencing. And you can see that the blue is the forward difference method. So if you use the forward difference method, the optimal for differencing this function, where let me zoom in a little bit. This is saying, open image in new tab. So what this is saying is it's differentiating the function that is f of x equals x of x plus sine of x, just an example function. And at right around 1e minus 18, which is square root of the floating point epsilon for the floating point numbers, right? This is our theory, right? That's going to be the best spot, and there you go. There it is, the best spot, right? For the forward difference method. For the central difference method, should be, if I remember correctly, it should be around the cube root of epsilon, which should be around, no, is it going to be like 1 minus the cube root of epsilon? That is going to be the, well, yeah, it's the opposite of this. So it should be like 1e minus 10, if I remember correctly. Right, so you have 16, the cube root of epsilon's 1e minus 6, and so the 1e minus 10 is going to be the optimal spot. And if you look at this, compare it to theory, or yeah, actually, oh, it was the 1e minus, sorry. And at the 1e minus 6, there it goes. That's kind of the optimal point for the error. So that is the cube root of epsilon. So that's the amount of error you should expect when doing finite differencing on f of x equals x of x plus sine of x, right? So you're differentiating this number. Which value of epsilon should you choose, right? So this is f of x plus h minus f of x divided by h. They're using h instead of epsilon. And what we see is that if you say, oh, I want to make epsilon go to 0, well, below that value, you're actually increasing the amount of error until you actually have O of 1 error. You have error about the size of x if you make epsilon be close to 0. And why is that the case? You're dropping off all your digits. Now, what is this black thing over here? Well, this is the complex step derivative. So the complex step derivative is a fun example. It's not used too much in practice anymore, but it's a good trick to know. And it is really going to be the case that brings us towards automatic differentiation, right? Because there's something else going on in here where they basically found a way to get to 0 error. Let's find out how to do that. So, okay, differencing in a different dimension, complex step differentiation. So the problem with finite differencing is that we take this really big number, right? We take this really big number and we subtract a really small number from it. That is not an operation that we want to do, right? We saw with floating point arithmetic that that's absolutely terrible. So instead, what we would need to do is we need to keep the number for what we're doing the derivative by. We need to keep that as a separate 64-bit floating point number, right? We want 64 bits for our value, and we want 64 bits for our derivative. So a way to do that is to use imaginary numbers, right? Why would that work? Well, because remember, an imaginary number is not one 64-bit number, it's two 64-bit numbers. So, so to see this trick, assume that, so we want to calculate, so let's say we want to calculate f of x, where x is a, let me do this inside of Lix. So what we want to do is calculate f of x, where x is a real number. All right, so we want to calculate f prime of x, where x is a real number, and f is a function from math BBR, right arrow math BBR, right? So we want to do a computation in just the real numbers, but f of x is analytic, right? So that means it has a convergent Taylor series, or its derivative exists in the complex sense. If you don't know what analytic means or holomorphic means for a complex function, it just means the derivative exists in some nice sense. So assume that it's a nice function, which is true for things like sine, cosine, exponential, all those things, right? That means it has a Taylor series. So let's do a Taylor series with a small perturbation in the complex direction, right? So this is our idea. We're like, let's do f of x plus. Oh, I guess the notes went to h now. Sorry about that. So we'll use h as a really small number. We want to keep h separate from x, right? We don't want to do this because then floating point numbers will not be able to represent the addition. So let's do f of x plus ih. So that way it's in a different 64-bit number. And now we just do the Taylor series, right? F of x plus f prime of x, h, right? So remember, so we're expanding this function around x, which means that its difference is going to be, well, so that means that this first thing here is going to be a polynomial that is x plus ih minus x, which is going to be ih, right? So that is the factor that's in front. Plus something that's math cal O of h squared, right? So that's a Taylor series expansion. Well, that's all we actually needed. So let's rearrange this. So f of x plus IH. So I f of x, I prime f of x. So let's isolate the derivative. The derivative in the imaginary times the derivative equals fraction f of x plus IH minus f of x divided by h plus math cal O of h, right? Now it's O of h because we divided by h. And I claim that we're done, right? Because f is a function from a real number to a real number. And so this means that that means that this is a real number. Let's take the imaginary part of both sides. If we take the imaginary part of both sides, well, x is a real number, and this is a function from real numbers to real numbers, so f prime of x is a real number. So if we take the imaginary part of I times f prime of x, the imaginary part is f prime of x, right? Because the real part is 0 because it's a real number multiplied by I, right? So that's the imaginary part there. Well, now we want to do the imaginary part of this. Right, so the imaginary part of the numerator divided by, well, that's just dividing by a real number, so that's the imaginary part. Um, it's just going to be multiplied by 1 divided by h, so we'd multiply the imaginary part by 1 divided by h as well, so we just factor that out, right? So plus math cal O of h. Now, this is a real function, right? This is f of x. So f of x is a real number. Real number divided by real number. Its imaginary part is 0. So there you go. And aha, this is a formula for the derivative, right? Let's read this off. You take your function f, you put in there x plus IH, you take the imaginary part, you divide by h, and that is an approximation for the derivative. It feels weird, right? But I mean, this is the proof. This is the whole proof, right? If h is sufficiently small, then you put x in there and you add your perturbation in a different dimension in the complex plane. You then calculate f on it and you take the perturbation part, right? You take the perturbation part and then you divide by h, and that is a correct calculation of the derivative. And that's precisely what's being done for this very good version. And why does it not have round-off error? Well, because this is a 128-bit number where you have x in one portion and you have h in the other portion. You redefine your function f to work on the complex numbers, and in the complex plane, it will keep the small numbers separate from the big numbers, and that makes it so that way they never end up canceling each other out. They never have this floating point error situation. So then all you do is you take a small enough h, and there you go. You have a very good calculation for the derivative. This is where automatic differentiation is going to start from, right? This key idea is that you want to propagate your derivatives along your computation, not inside of the same floating point number that you were doing the computation on, but in a separate floating point number that is doing a mirror computation in like the derivative space. So this is where derivatives as nilpotent sensitivities comes in. So right. So what we want to do is we want to measure how we're looking with a function by looking at it as f of a plus epsilon is something with a value portion and an epsilon portion. Right. So we can build an arithmetic, right? We want a number such that we want to start using two-dimensional numbers or higher dimensional numbers, where the first part of the number is what we call the value, and the second part is what we call the derivative, right? And so this is a two-dimensional number, right? So a lot like a complex number is a two-dimensional number. We want to think about epsilon as a signifier of a dimension, just like I is. And we want to start doing an arithmetic on these higher dimensional numbers that will start to give us the derivatives. We know this should start to work out because this shows that you can do this kind of algebra with complex numbers, but can we expand this to non-analytic complex functions? And so the key for defining the rules here is actually going to come from something called smooth infinitesimal analysis. There's another way you can justify this in if so for example, let's say you were to do f of x equals 2x squared plus x, right? Then if we were to do the definition of the derivative, right, we'd get the limit as x right arrow goes to 0 of f of x plus epsilon. Oh, sorry, epsilon. So if you do the definition of the derivative, minus f of x divided by epsilon, right, on this function, we write it out. What we get is 2x, 2x plus epsilon squared plus x plus epsilon minus x, and then we divide by epsilon, right? Now we do this again, we simplify, so we get 2x squared plus 2 4 epsilon to 4x epsilon plus epsilon squared plus x minus x plus epsilon divided by epsilon, right? So then we still have this limit here, right? So let's just do this out to see where this comes from. And then well, now let's take let's take the limit, right? So this now says that this part doesn't have an epsilon, right? So this is let's see, did I do something wrong here? Oh, so we should have evaluated this as 2x squared minus fx. Yeah. So this portion is going to get canceled out. So now we divide everything by epsilon, and what we have is then we have the limit as epsilon goes to 0, right? Limit as epsilon goes to 0 of this function that is no longer a fraction. It's 4x plus epsilon 4x plus epsilon plus 1, right? And that should be the derivative of this function, right? So this comes down 4x plus 1, right? When we then delete this value, right? That's going to be the last step. We delete that value. All right, so then it's going to be 4x plus 1 because epsilon goes to 0, right? So this is the computation for the derivative that you must know already, right? But let's look at it a little bit differently, right? The rule for this is you have an epsilon portion, right? Any portion that has an epsilon is the derivative. Any portion that gets an epsilon squared is a 0. Why is that the case? Well, because you're going to only be dividing by epsilon, and you take the limit as epsilon goes to 0, so it's a 0. If you ever see epsilon squared, it's a 0. And so what you can do is you can actually define an arithmetic where epsilon is a value that actually is carrying the derivative term as you go through a computation. Whenever you see epsilon squared, you instantly put it to 0. And it is not something that's an approximation, like a Taylor series approximation to the derivative. You can go back to your definition of the derivative and you can show that this is a valid, different definition of the derivative that calculates all the same things. It's called smooth infinitesimal analysis. So this is a form of analysis that uses it uses infinitesimals to do calculus, right? Well, in order for this to be true, you have to do the law. You have to exclude the law of the excluded middle, so you can't do proof by contradictions anymore. So it's kind of like a weird branch of mathematics. But if you want to see the formalization of it, you can. And essentially, you can make epsilons be a real infinitesimal number, and you can justify this process. And so let's use that result, that analytic result, that you can do computations just by thinking about epsilon squared equals 0, and by thinking about numbers in terms of their real part and their epsilon part. right? So what this means is we can represent a number in terms of having a a value and a derivative. And a derivative has an epsilon part, and our algebra is just whenever you do the operations, kind of like it is, multiplying complex numbers and such. But whenever you see epsilon squared, just make it a 0. So we define our number in just that way. And if we have two functions, f and g, well, what we can do is we can just do the algebra on that, right? So we can say f plus g equals, well, we add the not we add the value parts, and we add the dual parts, right, or the derivative parts. Notice that this is the same exact thing as the sum rule. We can do the product between two dual numbers. What's the product defined as? Well, you take, you have to FOIL it, right? So you would do, you know, um, f of a plus f prime of a times epsilon, right? So this is one number, and then this is another number. So now we do plus, oops. So then we do this number plus we do g of a plus g prime epsilon, right? And what do? Well, if I made this equal to an I, if this was an I, you'd know what to do, right? You just FOIL it, and then you would take the result, where whenever you saw an I squared, you turn that into a -1, right? But now let's do that with epsilons, right? Where we have this new algebra rule where whenever we see an epsilon squared, we make it a 0, right? If you do that, you write it down, and you get f of a times g of a, or you get f of a g of a, plus, you know, f prime of a g of a plus g prime of a f of a. This is all multiplied by epsilon, and then we have then we have the f prime of a g prime of a epsilon squared term, right? And now we just make this term equal to 0 because it has an epsilon squared, right? So this is our arithmetic. So when we do multiplication between dual numbers, what we do is we do the multiplication of the values, and then we do the product rule in the derivative portion, right? Where does this match up with what we did? Well, if you go through the actual derivation of the product rule, you'll see that the same exact thing happens, right? Where you get this epsilon squared term on the two parts that would be the derivatives multiplied by each other, and then you just zero it, right? So this is exactly the same thing as the derivation for the product rule, just done through an algebra instead of an analytic process. So let's start to do arithmetic with dual numbers to tell us how, or to show us how automatic differentiation works in practice, right? One of the cool things with Julia is that we can actually build an efficient automatic differentiation package in a lecture. Like in an hour of this lecture, we will have a working automatic differentiation package. I think it's actually about 20 minutes away, right? So, there's interactive utils just for using Weave. So let's define our dual number, right? All right, so now let's do dual number arithmetic with fast code, defining it in Julia, and show how this can give us a way to get accurate derivatives. So let's define a dual number type to start. It has a value portion and a derivative portion, right? Because you need to have the value and the epsilon. Right, so there you go. We have a number that has two portions. We parameterize it on the type. That way, for example, if this is t is a float 64, then this is a 128-bit number that has two portions that separates the value and the derivative. And now we import some operations from base, and we redefine them to do our dual number arithmetic. So our dual number arithmetic was defined here. So what we do is we say, base a plus, what we should define as plus between two dual numbers is going to be, well, we add the value portions, and then we add the derivative portions, right? And now how do we treat a number, right? So if a number is like a float 64, how do we treat it in this arithmetic of dual numbers? Well, alpha is as a number is equal to alpha and 0, right? Because a constant is something that doesn't have a derivative associated with it. right? So we treat all of our constants as though they have a zero derivative portion, and that's how we get this definition. Um, just in case you want to be cool, you can also use this way to define the operators in Julia. I mean, it's cool, but it's used so rare that I don't generally recommend it. But if you want to, this is a valid syntax, and people who write a lot of derivative rules, they do make use of this. Um, so yeah, so you can also define the subtraction rule, right, which is the similar, right? What is the product rule? Well, we define the product rule. So, what it's a dual number where you multiply the two values to get the value portion, and then you multiply the derivative times the value and the value times the derivative. Well, now you treat alpha as a dual number with a value and no derivative portion. You simplify the computation and you get this rule. This rule is really just saying, well, we've already defined multiplication between alpha and f. So an easy fix for that is we just define the multiplication between a dual number and a number as the multiplication between a number and a dual number. And so then this calls this function right here, right? Quotient rule has a little bit more to it, right? So what is the value of the quotient? Well, you take the, f divided by g. And now, what is the quotient rule? Well, you can look at the quotient rule, right? It is f prime g minus f prime g minus g prime f divided by g squared. And that is then what you write here as the derivative, right? The same thing for when you have dealing with alpha, right? Alpha is a dual number where the derivative part is 0. So take this rule, make g prime equal to 0, and you get this written out, right? This one is fun, right? So now you can say, well, if I'm going to multiply by, or if I'm going to divide by alpha, that's the same as multiplying by 1 divided by alpha, which we can then use the product rule for, right? Because we've already defined what happens when you multiply f times a number, right? So f divided by a dual number divided by a number is taking the inverse of that number and then calling this rule, which is then flipping it around to call this rule, and that's how it's doing this dual number arithmetic, right? So it's just forwarding functions upon functions upon functions, using multiple dispatch to decide what to do between dual numbers and regular numbers. The last thing is, well, I mean, we could find a lot more operations, right? So, for example, what is the exponent? Well, the exponent can be exponent, where you're taking a dual number to the integer n, is the same thing as doing multiply n times, right? So we tell it that's the rule, and now it's able to do a dual number arithmetic on it because this is only using multiplication underneath the hood. It is saying that, f to the fifth power is f times f times f times f times f. And so, notice I put like implicit parentheses in there. And so, if that operation is only using multiply, then it's just using a whole bunch of the multiply operations, and there you go. That's a method for defining, the exponent with an integer. So we're done with a lot now, right? So we can start to do computations on them. So we say this is the number. It's a dual number with 3 and 4, and we add 2 of these dual numbers. We get another dual number that adds this portion and adds this portion together, right? So 5 plus 3 is 8. 4 plus 6 is 10. Multiplication, 5 times 3 is 15. The other part is the product rule. We can then start to chain these rules together, right? It's going to call the plus rule, then it's going to call the multiply rule. And there you go. Now it's doing all this. Is this performant, right? Because we're forwarding functions after functions after functions. Is this as a performant as if you wrote it out by hand? So let's actually write it out by hand, right? Let's do the addition case. We add everything by hand, right? So we taken these 4 numbers that are for the dual numbers, and we say instead of doing dual number arithmetic, we add these 2 portions and we add these 2 portions. We put them in a tuple, right? So that's pretty fast because it's literally saying that the right way to do this operation is just 2 additions. And if we do this with dual numbers instead, what we get is 2 additions. So boom, there's no overhead to defining these operations using this dual number arithmetic. What does the native code actually look like? What is the machine code on the system? Well, you can see that, this operation right here It's just doing something where it's doing two move operations, so it's moving two things off the stack. It's then doing two add operations and then putting them back onto the stack to build this tuple, right? So that is the one written out by hand. The one written out with dual numbers is actually a little bit better. So you see that's not exactly the same. What is v move? What is vp add? Well, this is vector move. This is vector add. And so I actually found out that because we're representing these dual numbers in a way where it has always value and derivative portions, it found out that if we're going to do this addition process where you add the two values and add the two derivatives, you can do those at the same time. So that stands for vector move and vector add. And that means, this is SIMD right here. So, we actually got a better assembler code from doing this. And if you do this in a large enough code, you'll actually be able to see that you actually get more performance, right? So it's not even that we didn't lose performance; we actually got more processor level parallelism out by using a dual number to represent this operation. Just a fun little fact. So you can do things without so why is this able to do it without overhead, right? um in some sense, when I call add here, or when I call this add, it needs to check and find out which add it needs to do, right? In fact, it's not even that easy, right? That methods of plus, um there are on my computer right now 489 methods for plus. It needs to find out which one is going to call before it actually does the real plus. So why is that something that's efficient, or is that really bad? Well, because we have type stability, right? Because we have type stability and we have type specialization, right? This knows that it's doing add of dual and dual. And so at compile time, it realizes that this is compiling down to just be the operation that is plus between two dual numbers. And then at compile time, it figures out just to replace it with this operation right here. And so this all happens at compile time. And so there's really no overhead to forwarding a bunch of functions together. It is just an abstraction that you can make use of for free. So this is what we call a zero cost abstraction, or actually a negative cost abstraction because we got SIMD out. Yay. So okay. So now let's start to define higher order primitives, right? We can do the same process. So the same way that we started defining like what would be the value part of adding two dual numbers together, the value part of multiplying two dual numbers together, right? You can do you do your calculus on this as a function of a, and then what you get is you get your value and your derivative portions for how the rule should be for the dual number. So if this is still seeming a little weird, and if you feel like you're not exactly getting how this gets back to calculating derivatives of a function, we'll get back to that in a sec. Right now we're just defining the algebra. And my claim will be in the next portion that if you define this algebra, then you'll get the correct value. You'll get the correct derivative out. So let's go a little bit further here. So let's define this higher order primitive. So, let's say we want to do the exponential of f. Exponential just stands for e to the f, right? So this is e to the f of x, right? Well, how do we define this object? Well, it has a value portion and a derivative portion. The value portion is just going to be calculate the exponential of f of x, right? The value portion always just pushes on the operation on the value. The derivative portion is going to be, this is always the case, it'll be defined by the chain rule, right? Because x of f of a is going to be defined by the chain rule, gives you the derivative of this function as f applied to a times the derivative of f of a, right? So we define this second portion, the epsilon, the rule for what to do on the epsilon part for an arbitrary function then is to do the chain rule. And so now we can calculate x of f, where f is a dual number. So why is this important, right? Like, how do we get this? This is a cool arithmetic. You define a bunch of multiplies, pluses, and xpiz, and does this actually give us something usable? So my claim is yes. So why can this give us something usable? Well, let's open up our handy dandy notebook. So if we do f of x plus epsilon, so like if we just literally put x plus epsilon into a function where this is a dual number, what should come out is, by definition, because of the chain rule, right? We've imposed that the chain rule always holds. So by the chain rule, what we should get is f of x plus f prime of x times epsilon. if we had a, why is this just times epsilon, right? When when we did something like this, there was an f times dir. Well, dir is equal to 1, right? If we just think about this as x plus 1 epsilon, right? So if we do this, like, and we do the chain rule and everything, if we do this to an arbitrary f, what will happen from this arithmetic is that your value portion will calculate the value of the, this will calculate the value of the program, the same output as what happened if you didn't use dual numbers at all, right? And you see, like, every single time we did an operation, we just kept on forwarding that same operation there. So that one is easy, right? Um, but now, since we've defined every single time that we encounter something in this portion, we always do something that's compatible with the chain rule. And so what comes out is going to be that on an arbitrary function, it follows the chain rule. And so if we do x plus 1 epsilon, what will come out here is f prime of x will be in the epsilon portion. And so if you put this, if you put a dual number into a function f, or if you take a real number, you add a dual number portion where the derivative portion is 1, then what you get as the derivative portion of the output is the derivative of that function. You can immediately see it in the exponential case, right? Because here, if I'm to put in here, right, so if I define, like, x equals a dual number of 1 and or of 22.2 and 1, right? What I calculate is, x of x equals, hold on here, exp of x equals, well, this is going to be exp of 2.2 plus there's going to be an epsilon portion, which is going to be exp, well, this is the rule right here. It's going to be the exponential of the value 2.2 times epsilon. And so if we take the derivative portion of the output, what we see is that this is the derivative of the function. And by the chain rule, this is always going to be true. That's my claim. I'm not going to prove it here. I don't. Yeah, it's tedious, but essentially that's the reason, right? So under this algebra, if we represent a plus epsilon as dual of epsilon of a1, then because of the chain rule, if we put this dual number into an arbitrary function, what it will spit out is f of a and f prime of a. And this is true because of the arithmetic that we define. So this is a two-dimensional number, right? This is a two-dimensional number, but if we stick this into arbitrary functions, it will calculate derivatives. It will calculate the original output of the program, and it will calculate the derivative of the program with respect to the input value simultaneously, by changing the arithmetic. So let's actually see this in action, right? We've already defined enough portions to do this. So let's do this on the dual number that we've defined. So how does it do squaring here, right? It does squaring by turning this into x times x and doing the product rule, and then adding 2 plus epsilon 0, right? So it knows how to do this. And so if we let xx be the dual of a1, then when we calculate h on xx, this should be an output that is the solution of h of a, and then the second portion should be h prime of a. So let's look at this, right? So a equals 3, and so we do 3 squared plus 2 is equal, or 3 squared plus 2 is 9 plus 2, which is equal to 11. Now what's the derivative going to be? Well, the derivative is just 2x, right? Where x equals a, and so the derivative portion is 6. There you go. This arithmetic on this function, right? You put this dual number in, and it spits out a dual number where the first part is the solution of the equation, or of the function, the solution with respect to a. The second part is the derivative of the original function with respect to this value right here. You have to put a 1 here, right? Because that's what I was showing in that handy dandy notebook. You have to put a 1 here, because if you do this where you put a 2 here and you look at the chain rule, right? The chain rule, the rules that we did here, right? How we were doing these operations you would have actually had to put the 2 right here. So my claim is if this arithmetic is making sense, and this is always doing the chain rule, right? The chain rule here would be multiplying by 2, and so you should get 2 times f prime of x times epsilon in the derivative portion. Let's double check this. So if I do 2 here, then I should get my derivative value should be incorrectly be twice the value, and it is 12. Right? So, okay, that might be a little fast. You might want to go over this a few extra times if you haven't seen it before. But this number, because we defined it to do the chain rule correctly, it is a number such that when we put dual of a1 into arbitrary functions, the output dual number is f of a, the derivative portion is f prime of a. And so this is something where, it's analogous to complex step differentiation. It's not using complex numbers. You don't have to require that your numbers are complex analytic functions. And this will this will calculate accurate derivatives without round-off error because it is keeping the value portion and the derivative portion separate. So the same reason why the complex step differentiation was accurate, this is the same reason here. In fact, what we've done is we've hard-coded analytical solutions to derivatives at every step of the process. And so this is essentially the limit as epsilon goes to 0 that we get out here. This is going to be an accurate derivative. With respect to, you will get a little bit of floating point error, but the floating point error here will have no mismatch size numbers, and so the amount of floating point error that you have in the derivative term is going to be about the same amount of error as you have in your original function itself. Not a lot more error than finite difference method, but about the original amount of error. So we can write a function that actually calculates the derivative of an arbitrary Julia function, right? It has to be a Julia function because this is a compiler trick, right? We're taking the user's function, we're recompiling it to do dual number arithmetic, right? It is doing this arithmetic under the hood where we showed that one example where it has a different assembly, right? This is no longer just an add. It is 2 adds put together with a SIMD operation in there, right? So we need to recompile their function to do dual number arithmetic, right? And then we take the derivative of the output. So let's look at this again. We want to calculate the derivative of f with respect to x. So what we do is we define a dual number, which is x, and 1 of x. What is 1 of x? Well, 1 is this function that turns 1 of the same type. So 1 of 1.0 is 1.0. 1 of 1f0 is 1f0. 1 of 2f0. So let me actually do this on 2 because it'll be more clear. So 2.0 is a float 64. 1 of 2.0 is 1.0. Float 64. 2f0 is a float 32. 1 of 2f0 is 1.0. Right? So this is just giving us a 1 that is of the same type. Why do we want it to be the same type? Well, because we said that the dual number needs to have the same type for the value and derivative portions. So so this is something that is key to generic programming, right? When we talk about writing these functions that is independent or that works with the user's input types and not hard coding details. This would be hard coding a detail that this is something that works on float 64s. Or you can do it on float 32s, right? And you can hard code versions that work for both of them. Or you can say any possible number type that has defined a number that tells me what the number 1 is. Use that one for this. And this will work on any number type. It'll work on complex numbers. It'll work on quaternions. This is a way to take the derivative of anything in the world. That is a pure Julia code, right? Why does it need to be a pure Julia code? Because it needs a dispatch f of a dual number, and it needs to be able to compile and build the new version that will do the function on dual numbers. And now when we do this computation, the derivative portion of that dual number outputted is going to be the actual derivative we want. And so we just take the derivative portion. So this right here is a function that does automatic differentiation of Julia functions that are defined using the primitives that we have. And so we can, take derivatives of functions, and there you go. These are accurate, fast derivatives using extra SIMD and everything because of this automatic differentiation that we defined. We could even take derivatives of other functions, right? So a lot of functions in Julia have fallback definitions where if you give it, if you say like, oh, I have to do, square root on a number, how would I define square root on a number? Well, you have this definition where you can find the square root by using this iterative process. You look at it, Wikipedia, you'll see that, this is one of the definitions of the square root. It's the limit as I goes to infinity of doing this repeated process. And so what is the square root of 2.0? It is 1.1, right? So this is just the square root of 2. So this is a very nice way to calculate square root of 2. But this is only using multiply, plus, and divide. And so it is compatible with our dual numbers, right? So let's actually look at what happens if you do floating point derivative, right? So this is f of x plus epsilon minus f of x divided by epsilon. This gives you a derivative value of 0.353, da 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 da. Our dual numbers can do this too, right? So when we output this, we have the value, which is the square root of 2, and we have the derivative, which is 353, 553, etc., right? This is going to be more exact than this one because this other one has round-off error, but you see that they're going to be correct. They're going to be the same for about 8 digits. So a lot, like it looks like, oh, you don't just hand wave here. Don't just kind of be like, oh, they look kind of correct. Like, count the digits. This is correct to about 8 digits. This is going to be the same to about 8 digits because of the theory from that we described earlier, right? So okay, that's pretty cool. We have a way to calculate derivatives of functions as long as they're written in the primitives that we've defined. And then what we showed how to do is you use the chain rule to define new primitives, right? And so this is actually where some libraries in Julia come from, right? So for the automatic differentiation space, the automatic differentiation directly works on Julia functions, and this is really a key difference from something um, like AutoGrad or something like TensorFlow or PyTorch, right? TensorFlow needs to build its own computational graph because it's defined its rules on its TensorFlow graphs, right? When you do operations in PyTorch that are using PyTorch arrays, the reason why it forces you to use a PyTorch array is because it's building its own graph object and it has defined derivative rules on that graph object, right? With Julia, because of the way that it interacts with multiple dispatch, the derivatives are actually defined on the Julia functions themselves. So you don't need to use a library to have something compatible with automatic differentiation. Instead, what you do is you define libraries like diffrules.jl. So diffrules.jl just defines a whole bunch of rules for how do you do, let's see, how do you do things like logs, cosines, sines. And so when you use an automatic differentiation package, it knows this is where all the scalar rules come from. If you want to use digamma functions or anything, and almost every function that is almost every function is built up from these core pieces. If you want to use a library for automatic differentiation in machine learning, right, you also have these array-based primitives, and we'll show how to define them in a sec. These are all defined in the library chainrules.jl, and you'll see that it's just defining dispatches on it's just defining dispatches on Julia functions that tell it how to do the derivative of log det, the derivative of how to do log abs det. So det is the determinant, and so all these functions are defining these kinds of primitives for everything that they can do or everything that it seems like you can build a better version of. So it's the pseudo inverse of a matrix. All these things have derivative rules on them, and that's why Flux is able to work directly on just Julia code, right? There's no machine learning library that you have to use to do with automatic differentiation. It just actually just automatic differentiates Julia code because these rules are defined right there on the code that you're using. So you almost have enough knowledge now to be able to go into this library and add new rules yourself. Actually, but before I move on, if you do want to look into that, and that's actually a whole load of very nice final projects. Could just be to take some papers in this domain and say I want to define chain rules for reverse rules. We'll get to them. Forward rules. This is a multi-dimensional forward rule, which we'll define in a second here. you defining a bunch of rules using papers for how you do things like what is the derivative of an eigenvalue solver. These things you can define through chain rules, and you can find the papers for them. Those would be some very nice projects to do very high performance implementation of them. Just a thought. So okay, so how do we do derivatives in higher dimensions, right? This is going to be something that all these rules in machine learning and everything are doing things on arrays. So how do we do things on input functions with multiple inputs? And multiple inputs is another way to represent a function on arrays, right? So let's get to this. So how do we define the derivative of a function f of xy? Um, Well, you can't in general, right? But you can define two derivatives, right? You can define the derivative with respect to x and the derivative with respect to y. So those are your partial derivatives, right? So the way to be able to do higher dimensional automatic differentiation automatic differentiation of functions with multiple inputs and multiple outputs is you just do the derivatives on the different directions one at a time, which is essentially how you have to calculate derivatives, right? Derivatives are always directional. You just have to choose which directions you want to choose or you want to differentiate by. Um, so for example, you can so here we define the function ff. Here we define the function ab, or now we define ab. We can define a single variable function, right? This is what we call a closure. We can define a single variable function which is enclosed at the value b, right? So then we can calculate what is the partial derivative of ff at the value a, or at the value a, the derivative of ff with respect to x at the value ab is the derivative of the value ff1 at a, where ff1 has already enclosed the value b in. Right. So another way of writing this is so x goes to ff of xb, right? So this is canonically what people call closure. So we're making it so that we're returning a multivariable function into a single variable function, and then we're calculating the derivative in that direction, and this will give us a partial derivative. Right. So so dff dA or dff dx at the point AB is equal to 10.0, right? So that is a partial derivative of a two input function. Okay. Under the hood, what is this doing? So this is doing the dual number here, and this is doing a normal number here, which is the same as doing dual of a 0 of or dual of b, 0 of b. Right, so it's essentially doing this operation. It's up anytime that it runs into something that's not a dual number, right? It turns it into the dual number to do the arithmetic on it. So let's keep that in mind, right? So we turn this into a dual number with a 1 here and a 0 here to do the partial derivative with respect to this value, right? So to do the derivative with respect to the other value, then we turn this into a dual number where this one has a dual portion of 0, this one has a dual portion of 1, and now we have two outputs, right? That one of those is the f prime of x, or df dx. The other is partial f partial y, right? So we have to, in order to calculate the gradient, right? So gradient, remember, is grad f is equal to this vector, which is df dx, df dy, right? Well, how do we calculate this? Well, we do two derivative computations, and then we take, we take that first one, we put it here, we take the second one, we put it here, and so this takes two differentiations in order to do it with forward mode. We'll see that where we get to reverse mode automatic differentiation is that there is a way to calculate gradients with one function call. But with forward mode automatic differentiation, the number of times that you have to do derivative is equal to the number of input spaces. We can relax that a little bit, though, right? So the way that you can relax that is, right, so what you really want to do is you want to do the directional derivative in different partial directions, right? So let's kind of computationally write this down a little bit. Right. So what we wanted to do is we wanted to calculate FF of dual AB, right? And then we want to do dual 0 of B, right? So we want to do this with a 1, this with a 0. To make things simpler, I'm just going to make this 1 and 0, right? So we want to do this operation, and then we want to do this operation. And then this array right here, this array is the gradient, right? So this array right here is the gradient, right? Because this is the derivative with respect to, and then we take the derivative value and we take the derivative value. This right here calculates the gradient, sorry. Right. Because this first one is the derivative with respect to the first input, this one's the derivative with respect to the second input. So now, could we do both calculations at the same time, right? Well, we're allowed to define our own arithmetic, so let's just do it, right? So let's actually what we can do here is we can say, I can do a dual number with more dual numbers, right? I can do something like, let me write down the solution, and then right, so I can do it so that way I don't just have one epsilon, I can have two epsilons. I can have, one here. So that way I kind of combine those two computations. Right. And now the number that comes out of here should have it should have a value portion and two derivatives, where the first one is the partial with respect to the first value, second one is partial with respect to the second value. How do I define this arithmetic? Well, what I would do is I just say, well, whenever I get a cross term, right? So I want these two computations to be entirely separate, right? Because here I'm doing the two computations entirely separate. But what I want the value part of the computation to be the same, but I want to do the two derivative computations completely separate. So what I can do is I can say whenever I have epsilon times epsilon2, that's an overlap. And that overlap between the derivatives make that equal to 0. Now I define I squared equal to 0. And that's the whole rule set for how you define this higher dimensional differentiation. Right, so this is the same idea. What we're doing is we're doing a multidimensional Taylor expansion, and we're using the directional derivative against a vector of epsilons. So you can then do your partial, you can look at the product rule, look at all these different rules in terms of this whole vector of epsilons. So now you can use a whole static vector, right? So remember we talked about static vectors. So this is a multi-dual with exactly n dimensions. And with n dimensions, we can take all of our derivative values and add them up, because that's, all the derivative values. In some of these rules, you have to get a lot more complicated when they're multidimensional, but this is the idea. Right, the idea is that we're just going to make the computation in this dimension separate from the computation in this dimension, but do them simultaneously. So when this dual number goes into the computer, right, it will be doing 3 operations at a time. It will be calculating the value of the program, the derivative with respect to the first input, and the derivative with respect to the second input simultaneously. This is actually a little bit faster than doing it completely independently. Why is that the case? Well, because remember, whenever you do a dual number arithmetic, and whenever you're doing computations on dual numbers, you always have to be defining what goes on in the value portion, right? So if you actually do the computation with two different dual numbers, right, we'll do the value calculation, which is also known as the primal calculation. It'll do the primal calculation twice, where this is using the same primal calculation to do the differentiation with respect to both axes. Right. So it is a slightly more efficient way of doing it. And then here's the chunky details for how do you define a multidimensional dual number. So let's pull this in. So we define what is plus, what is multiply on these multidimensional dual numbers, and in the same way, now we can now we can say, well, let's let a and b be 1 and 2. Let's define multidimensional dual numbers. Right? Notice that we start this one with a 1, this one with a 0, this one with a 0, this one with a 1. So the first output will be the partial of g with respect to x. The second output will be the partial of g with respect to y. And now we have a multi-dual number which calculates the value of the computation, and it outputs the derivative with respect to x and the derivative with respect to y. So now we can calculate Jacobians and gradients and everything using just arithmetic, right? These higher order operations can just be, well, so here I have ff is a function with 2 inputs and 2 outputs, right? And now how do we define the Jacobian? Well, remember that the Jacobian is df dx, or df1 dx, df1 dy, df2 dx, df2 dy, right? So now if we actually look at this, what we see is that you know this is the dual number that is output from the first function. This is the dual number that is output from the second function, right? And so remember that when we do dual number arithmetic, that this first value, because this is the derivative in the direction of x and not in the direction of y. This first value is the df1 dx, df2 dx, df1 dy, and df2 dy. So this matrix right here, 2, 1, 4, 0, 2, 1, 4, 1 is the Jacobian of this multidimensional function. Right, and so we can also do gradients. So gradients are functions from Rn to R1, and so that's actually a subset of this, right? Where this is actually that's actually a subset of this, where you have only one output, but you have many different inputs. But it's the same idea, right? That array that comes out from doing all these different partials is the gradient when you transpose it. Yeah. And so if you want an implementation of this that is very usable and is widely used throughout Julia, you can take a look at forwarddiff.jl. And it is an implementation of forward mode automatic differentiation through high dimensional partial dual numbers. So it uses this trick of representing multi-duals, and it pushes these multi-duals through a program. If you tell it to take the gradient or you tell it to take the Jacobian of your function, it is getting this solution by using exactly the arithmetic that I've shown. So that's what we want from this course, right? Like, this is how the library is built. Like, this should not be a black box. This is what's going on under the black box. But understanding automatic differentiation from this point of view gives us actually a lot more ammo. So, okay, so what is this dual number actually doing? I want to give you a different definition in the multidimensional sense. So when for a function f of x, f has n inputs and has one output, right? Another way to think of a function that has n inputs and one output is one portion of a multidimensional function, right? R2 to R2 function. If you take the top portion of that, or the first element of the array in the output, that is an Rn to Rm function, right? And that's just something to keep in mind. The basic operation that you're always calculating whenever you're doing higher dimensional calculus is you're always doing a directional derivative, right? So, like, this is the basic operation. F of x plus epsilon v minus epsilon minus f of x divided by epsilon is the directional derivative in the in multiplied by the directional vector x, right? So why do we talk about partial derivatives when if I'm saying that this is the core, the only thing that you need to really know? Well, partial derivatives are the directional derivative with respect to the basis function, right? If you let v be the vector that is 1, 0 or 0, 1, then when it's 1, 0, this is the derivative with respect to the first basis component. When it's 0, 1, this is the derivative with respect to the second basis component. So partial derivatives are directional derivatives in the direction of the basis functions. And so, if we want to do directional derivatives with dual numbers, right? Then if we look at what actually happens here, with dual number arithmetic. So let's look at f of x, y, right? So f of x, y equals x squared plus times sine of y. Now let's put dual numbers in here, right? So we have a value portion and a derivative portion, value portion and a derivative portion. What you see comes out of here if you do this arithmetic where you just kind of start plugging in these rules and the chain rules, right? What you get from dual number arithmetic is the directional derivative at AB, where this is telling you the direction to calculate the derivative. Let's go up a little bit, right? So what we were actually saying here when we did, so this is another interpretation of what we had just did, right? So we understood it one way, now let's understand it another way, right? When we say ff of make the first thing a dual number, make the second thing be not a dual number, and that will change it automatically to be dual of b, 0. What this is actually doing is saying that this dual number, right? Like, so this means that we're having a input value that is a vector that is ab, right? And then we're calculating and then the vector for the derivative is 1, 0, right? Which means that we're calculating the derivative in the direction of x, which is the partial derivative with respect to x. Now, when we change this around to be 0.0 and 1.0, right, then we're still calculating f of ab, ff of ab. It's a function that takes in two things, but now the vector for the derivative, like the direction vector, is 0, 1, and so it gives us the partial derivative with respect to y, right? So, I mean, we had a different explanation for how we got there, but this is a different way to think about this higher dimensional derivative, right? So, in this sense, the first derivative is being defined as the directional derivative with respect to x, and the second one is the directional derivative with respect to y. And so the outputs of our function, right? The output of our function is the directional derivative with respect to x is the first portion, and the directional derivative with respect to y is the second portion, right? And so we take these two columns, we can concatenate them together, and that's the Jacobian. So actually, another way of writing it in the Jacobian is that the Jacobian is the matrix where the first vector is the directional derivative with respect to x, the second column is the directional derivative with respect to y, the third column is the directional derivative with respect to z, right? And that's how the Jacobian is if you're to think about it vector wise, right? But then that means that in a higher dimensional sense, there's no reason that this actually had to be an arithmetic about taking partial derivatives, right? That was because we chose ones and zeros in our basis in our derivative elements. We can actually take arbitrary v, so we can take a direction, right? If we define these dual numbers, for example, to be, if we take a multi-dual number and we define this to be, 1, 1 and 0, 1, then we get a different computation, right? You get a different computation where this right here is the directional derivative of ff with respect to the vector 1, 1, and then this right here is the directional derivative with respect to the vector 0, 1, which is the partial derivative with respect to y. Hopefully I'm returning all these values back to the right things for the notes. But yeah. So this means that the core computation of what forward mode automatic differentiation is actually doing in higher order in this higher dimensional space is it's calculating directional derivatives. So like that is its thing. Like we could do this for Jacobians. Jacobians have their columns as directional derivatives by the basis functions. So we make it do a bunch of basis function directional derivatives, and it outputs the Jacobian, right? But there's nothing special about that. Those are just the basis functions. We can do this in any direction. And this is the key for understanding forward mode as actually a method for computing vector Jacobian products. So let's look at this a little bit. Right. So let's So note that another representation of the directional derivative is f prime of x times v, where f prime of x is the Jacobian, or the total derivative of f. Oops, let me write that in there. Or total derivative. All right, so you can also, if some places where you look it up, it will also call it the total derivative, right? So if we write it out in the standard basis, right? Let's actually write out so let's let J be this Jacobian term. Right, so let's let, I still have my little matrix up here. Yeah, so we have this thing like df1 dx, df2, or df1 dy, df2 dx, df1 df2 dy, right? So this is a Jacobian, right? So let's write it out in the standard basis where we do this is j, this is j, and we have v equal to v1, v2, right? So when we do this matrix vector multiplication, what we get is, well, we just do a matrix vector multiplication, right? So it's going to be row 1 times, well, let's write this as a column vector, right? So this is going to be row 1 times column 1, row 2 times column 2, and so this is going to give us the two values of wi. So this is going to be for the ith, for number I, we use row I, column I, and that gives us out the vector Jacobian product against the vector v, right? So now what we see is that, if we write in actually what this j term is, right? J of ij is going to be dfi by dfx, or these should be partial derivatives. I'll fix those later. So this is the partial derivative of f with respect to x times vj, which is exactly the directional derivative at x of the function fi, right? So this right here. So sorry, I misspoke earlier. The rows of the Jacobian are the directional, or yeah, the rows of Jacobians are directional derivatives, and the yeah. Oh, so the rows of Jacobians are gradients. The columns are directional derivatives. Yeah, and so what this shows is that if we want to calculate f prime of x times v, another way of doing that is to take the directional derivative of f with respect to the v direction. How could you do that? How could you do that very efficiently? Well, I mean, we have a way of doing that, right? So the way of doing that is just to define a dual number, right? We define our dual number where the input is this defined as this vector v, then the output in the derivative portion is the Jacobian times the vector v, right? So another way to think about what it's doing is that, what high order forward mode automatic differentiation is doing is you have this input value, right? So you input a value, and you input directional vectors, and what it spits out is the function applied to the value and the Jacobian at that value multiplied by the vector, the directional vector v1, the directional vector v2, and each of those different directional vectors are what show up in these different epsilon terms. Let's go back up to understand that, right? So here we wrote down a directional vector v1, directional vector v2, right? So this is the basis function 1, basis function 2, and so what comes out is the derivative with respect to, so this right here, 6.0, 2.0, is exactly the Jacobian of ff applied at x and y times the vector 1, 0. This is the Jacobian of ff times the vector 0, 1. That's this value right here. So another way to think about these things, they're both directional derivatives, and they're also the Jacobians times vectors. That's going to come into play very soon, because when we do Newton's method, we'll see that everything's about calculating vector Jacobian products. And so you can think about this as a nice trick, where if you needed to calculate multiplications of a Jacobian times a vector without ever forming the Jacobian, Dual number arithmetic is a computational way to recompile your program to give you exactly that. So without ever building the Jacobian, right? We never build we don't build Jacobians here. You know, that part of that dual number of the dual number part of the output of your program will be the Jacobian times a vector. Right? This thing right here is the Jacobian of the function applied at 5, 3 times the vector, where that vector is the vector that we put in as the dual numbers. Go back and rethink about it. This is equivalent to everything that we had said before. So now, in that sense, right, I showed you one way to think about calculating the Jacobian. In this new sense, where we're thinking about it as directional derivatives, right? Well, how do you calculate the Jacobian? The Jacobian matrix, remember, is where did I write this down this time? Darn it. Yeah, so this Jacobian matrix, remember, is the directional derivative in the x direction as the first column, the directional derivative in the y direction for the second column, etc. Right? And so if you want to calculate derivative, or if you want to calculate the Jacobian in one function call, what you do is you build this really big dual number where, if you have n inputs, then you have n epsilon terms. And you make this first epsilon term be 1, 0, 0, 0, 0, right? So E1, the basis vector 1, and then you have E2 be the basis vector 2, En be the basis vector n. And then if you put in this dual number, then what it will spit out is the Jacobian times E1, Jacobian times En, right? And all of these terms are just the Jacobian times the basis vector, which is precisely the directional derivatives, and so this will give you the input. Let's go back and look at what we saw before, right? So this right here is E1, E2, E3, right? Notice that this is E1, this is E2. So when we define our dual numbers to be E1, E2, the output of this is a dual number that has the first vector being Jacobian times E1, and the second one being Jacobian times E2, which is exactly the partial derivative, the directional derivative with respect to x, the directional derivative with respect to y, right? I'm saying the same thing in a bunch of different ways to be able to show all these different equivalences, because these are the tools that we'll be using, right? We'll be using forward mode automatic differentiation as a method for building Jacobians, but also as a method for calculating vector Jacobian products without calculating Jacobians. And so all of these things are all represented together. I tend to really like this way to think about it as, in the end, the arithmetic that we've defined does exactly this operation. Or when you put in a dual number that has all these epsilons in there, what it calculates is vector Jacobian products with respect to the different the different vectors that you had as inputs for the dual numbers. So if you have a dual number with a value portion and then v1 epsilon, then what you put that into your program, what it'll calculate is the solution of the program, the original solution with the value, and then the Jacobian of that function multiplied by that vector that you put in as the dual number. That will be your output in the derivative portion without calculating this Jacobian. So if you want to calculate the Jacobian, you just use the basis vectors as your inputs, and boom, you get out a Jacobian. But this is a much more versatile method than that. How do we get to doing things like, I showed chain rules.jl. What is that doing? Well, now what you're doing is you're saying, I'm going to represent my dual number as an array. So this is an array of numbers, and so then my value is going to be an array. My epsilon is going to be an array of, right? So let me write this down. So, okay. So let me begin to write this down. So now I have something like where, D is equal to, D1, D2, D3, etc., Dn, right? So this is it inside of if it was a real number, right? Now my dual number representation is that D0 is the value portion, right? The value portion is always the same. And now sigma is equal to something like D11, D21, right? So it's a whole matrix. . Right, I'm not going to write down, but it's a whole matrix. And why is this a whole matrix? Well, because we're going to multiply it, because we're going to say that we have an epsilon term here. We now have a whole vector of epsilon 1, epsilon 2, epsilon n, or epsilon m, right? Because we can take different numbers of directional derivatives than we have inputs. So we can make this be an m and have that be a different number, right? So now the way that we define this multidimensional dual number is we take this matrix, we multiply it out, and we get this. You can think about it as you take one of these dual numbers, d, and you stack it, right? You have an array of d's is equal to an array of these values plus this, plus this, plus this. And what you see on the right here is these coefficients in front. Those could just be those. If they were scalars, they would make the coefficients of a matrix. Right, so you can go up to here, what we did before, right? And instead of writing this out as a scalar and put them in an array, right? You can say that I have a dual number where I have an array a, b, and I have a dual portion which is 1, 1, 0, 0, 1, right? Like you can put this in. This would be the matrix of the dual number portion. So this is a different way to represent the higher order arithmetic. The chain rule, you define them in such a way that the chain rule holds. It's the same exact idea. If you do it like this, then notice that if you have the identity matrix be your derivative function, then the output of your operation is the Jacobian. And this is a really nice way to represent high order primitives, and this is how you can computationally write in primitives that work directly on arrays and with BLAS and with GPU as well. But it's still the exact same idea. So what about higher derivatives? Well, you can extend this idea to higher derivatives, right? So if you do want to keep higher derivatives, then you can have the epsilon cubed term be the one that's finally 0, and then you can write down your functions in a form where you keep an epsilon version and you keep an epsilon squared version, and you can show that the same idea holds. You do have to be careful because the second term of the Taylor series here is going to have a 1/2. And so whenever you take a value out of there, you have to multiply it by 2 because it's half of your directional, derivative. It's half of your mixed partial derivative, etc. But this is something that you call Taylor mode automatic differentiation, and so you can actually do entirely Taylor series mode, where you define a number type, where after you put that into your program, it outputs the first derivative, the second derivative, the third derivative, etc., as many as you want. So there are packages like Taylor series.jl, where if you use Taylor series.jl, it's defining these number types that are these high order Taylor numbers, and it does an efficient computation with accurate derivatives for functions to high derivative values using exactly this technique. So this has been a long lecture. Sorry about that. But what I want to end with now is how do we use this thing, right? So an application here is with to solving nonlinear equations with Newton's method. Right. So this is what you did in your homework, right? Where when you were dealing with Newton's method, what you have to do is you needed to calculate Jacobians, right? As part of your homework, you realize that there's this Jacobian you had to calculate in Newton's method. So what's a fast way to calculate Jacobians? You use automatic differentiation. So here, and what I'm showing is that you can use this function, you can use this package for Diff, which defines exactly the same automatic differentiation system that we defined here. It has more rules than what we defined in this lecture, but it's pretty much exactly the same under the hood. So, the way that you can do Newton's method, right, is you say, well, remember, what was Newton's method? Newton's method was xn plus 1 equals xn minus the Jacobian at xn inverse we'll be getting into the next lecture exactly how this works out, but let me just kind of showcase this. So times or divided by f of x, right? Or yeah, multiplied by f of x. So you have the inverse of the Jacobian times the function, right? And so this is the same thing as doing believe me here, this is what we'll be doing next lecture. This is the same as doing the Jacobian backslash f of x. That's equal there, and then we do xn minus that. So this is another way to be able to calculate Newton's method. So here we say calculate the Jacobian of f, and then do the update step. And if you do, this is a quick way to write Newton's method with automatic differentiation derivatives. And you see that this is something that converges to give you a zero of the function, where the function that we're looking for is x squared plus y squared minus 1, x minus y. And so one way to solve this is to you find that you need to have, this is these two values, when you square them, it's equal to 1, and then they're the same, so x minus y is satisfied, right? So this is a quick implementation of Newton's method, and it's able to handle a lot of different inputs because it's using automatic differentiation for the Jacobian to be fast. I'm going over this last portion really quickly because doing Newton's method will essentially be the entire next lecture. So let's keep it for that because this is already long. So in conclusion, this is forward mode automatic differentiation. It is a technique where we can take your program and we can recompile it to do a different arithmetic, where in this different arithmetic, everything is doing vector Jacobian products or Jacobian vector products, or what you can also think of as directional derivatives. And it is a way to be able to accurately calculate directional derivatives in a way that is fast and uses SIMD and all these cool properties. So now that we can get Jacobians and Jacobian vector products very easily, the next lecture will be how do we do Newton's method in an effective way for solving stiff ordinary differential equations.